So, good morning, everybody. Not just a Monday at 9 o'clock, but a rainy Monday. I feel sorry for that. Last time we looked at quantum scattering and at the energy exchange between the photon gas and the electron gas. Do you have any questions about what we said last time? Everything clear? Then I ask you to maybe prepare a little bit what we are going to do today. And this will be about radiative quantum transitions. So I'm showing the table of contents here. And we are going to jump into chapter 2.7. Chapter 2.7 and hopefully also chapter 2.8. Let's see about that. There were two things that I announced we would need from quantum mechanics, which I hope you have seen before. This is Fermi's golden rule and the perturbation operator, perturbation Hamiltonian operator due to electromagnetic radiation. I'm going to write this down and then we are going to discuss this. So, radiative quantum transitions. The point is that we need to understand spectral lines. So what is the probability with which a spectral line is formed? What are cross-sections for the formation of certain spectral lines? And what is the shape of spectral lines? These are the main questions that we are going to address. And of course, it will be possible to understand all of these questions and answer all of these questions with rather elementary quantum mechanics. But let me first write down the ingredients we are going to need. So capital gamma here is a rate. So this is a number of things per time. And these things are transitions. Between an initial state n and the final state m. Under the action of some perturbation operator that we will have to specify. And then, of course, we will need the absolute square of this because the absolute square of transition amplitudes gives the transition probability. Then we need a normalizing prefactor that's 2 pi over h bar square. And then we will have a Dirac delta function here identifying the precise frequency that corresponds to the energy difference between the two states n and m. So let me write this down as well. Omega n m is En minus Em divided by h bar. And if you take the other way around, right, Em minus En, then you can use a plus sign here and you will get the same result. This doesn't matter. This comes from the property that these perturbation operators are Hermitian, and so we do not have to worry about this line being an emission line or an absorption line. Okay. Fermi's golden rule. Have you seen that before? Who has not seen it before? Ah, lovely. Do you remember where this came from? Let me briefly sketch that because we will have to return to that anyway. Probably this equation looks familiar to you. If you do perturbation theory with that, quantum mechanical perturbation theory, you split the Hamiltonian into an unperturbed Hamiltonian H0 and a perturbation Hamiltonian H1, you expand the perturbed state psi into unperturbed states, so eigenstates of the unperturbed Hamiltonian, and you obtain, this means not immediately but after some work, you obtain an evolution equation for the coefficients multiplying the eigenstates of the unperturbed Hamiltonian in the perturbed state. And this evolution equation, I'm going to need this later, that's why I'm writing it down, looks like this, minus IH bar, this comes from dividing this over. Now, this is a V, this is an H1. I will need to explain how the two are related. That's the evolution equation of these coefficients. Under certain assumptions. The assumption is that state M is only weakly excited, right? So the system is mainly in state N. This is a condition under which this equation is derived. It usually works. I just wanted to point out this is not a precise conclusion, but a conclusion under the assumption that most atoms or whatever you have are in state N, and state M is only weakly occupied. Okay? Then I can write down this. Now, you see, if you just integrate that, right, you can just calculate what Cmn as a function of t is, and if you integrate over infinite time, you get this delta function that appears up there. Of course, you cannot integrate over infinite time. But infinite time means you integrate over a time period that is long compared to the time that the system needs for the quantum transition. And for that, you usually don't need very much patience. All right. So we will need this expression here, which directly comes from Schrödinger's equation and this perturbative expansion here. Now let me finally relate the V here to the H1. I'm going to write H1 in this way. In other words, I'm assuming that the perturbation Hamiltonian is periodic in time, that it has a period omega, that's of course the period of the, angular frequency omega, that's of course the angular frequency of the incident electromagnetic radiation that causes the perturbation. But I need to split this time dependence off in order to integrate this thing over time, and this is why I distinguish the V from the H1. Okay, so you see directly from Schrödinger's equation, you get this evolution equation here under the assumption that the excited state of the two states N and M is only weakly occupied. And then you integrate this thing over time and directly get Fermi's golden rule. Okay. That's one thing that we need from quantum mechanics. The other thing is the perturbation operator itself. And I'm claiming that I can write V as electron charge divided by MEC, electron mass times the speed of light, an amplitude A0 of the vector potential of the incident radiation, e to the I kx times a momentum that I write with a momentum operator that I write with a capital P, for reasons. All right. I'm claiming that this is the perturbation operator. Are you surprised, or do you know why? Who is surprised? Thank you for your honesty. It comes about like this. In an electromagnetic field, you see that you need to replace the momentum operator P. This is the one you know, right, from ordinary quantum mechanics, minus IH bar times the gradient in a spatial representation. So you need to replace this by that. Which is this. Does that look familiar? Right, that's the canonically conjugated momentum of a charge E minus E in an electromagnetic vector potential A. How does that come about? You take the Lagrange function of the free particle. This is just MEC square integral d tau. That would be a free particle without exposure to an electromagnetic field. And then in the electromagnetic field, you add this expression here, which couples the particle to the electromagnetic vector potential. All right? So here is what you do. You start with a Lagrange function of the free charged particle with mass ME, and then you couple that to the electromagnetic field by adding this typical coupling term between the electromagnetic potential and the current density. You might wonder, why is there a three-dimensional vector potential, not a four-dimensional one? We need a Lorentz invariant term. We gauged that away. Not so much you, but I gauged it away. Because in order to arrive at this here, I'm using a specific gauge. And the gauge is, first of all, diff A is 0, that's the Coulomb gauge. Then I have one gauge degree of freedom left. And I choose that to set the electrostatic potential to 0. And in that gauge, this is valid, otherwise I would have to write A mu J mu. That's also possible, but a complication here for our purposes. So that's the gauge we are using, and this is also important for the shape of the perturbation operator, as you will see. So that's one thing. Anything else? Okay, good. Now, if you accept that this is the canonically conjugate momentum operator of a particle in an electromagnetic field, then of course you have to square this, divide this by 2m. So this Hamiltonian, or this kinetic part of the Hamiltonian, it's not the complete Hamiltonian, it's going to change to capital P squared divided by 2me. Capital P is this thing here. And now I need to square that. So that will be P squared sorry, it should be minus Q, so plus E for an electron. So we have now I need to be careful, and if I square this term here, I will have one term P times A and another term A times P. they do not necessarily commute, because A may depend on spatial positions, and space and momentum do not commute. So I have to be careful what I'm doing. But the term P times A contains a divergence of A. So choosing this gauge means that I can neglect the term P times A. And then I can commute the two. Then I just get 2 times E times A times P. Okay, and of course I'm getting another term, E squared over C squared times A squared. And you see, obviously I'm dropping this term here, the term that is squared in the electromagnetic vector potential. Why can I do this? You see, we are accumulating approximations, and this will not be the end. Right? There will be others to follow. In order to see why I could neglect the third term here and leave the perturbation at that, let's estimate the magnitude of these terms. So let us compare. Let me write this as a vector here. It will depend on spatial positions, therefore also on the space operator, on the location operator. But let me just write this as a vector here in order to indicate that we are not in quantum electrodynamics, right? We are not quantizing the vector potential itself, but only the spatial dependence of the vector potential. All right. So I need to compare the expectation value of that to the expectation value of that for example, a hydrogen atom. If I am in this gauge here, then the electric field obviously cannot be just minus the gradient of the scalar potential. So it has to be minus 1 over c dTA. That's the time dependence of the vector potential, or the time derivative of the vector potential. But now I'm assuming that the vector potential depends harmonically on time. So I can write the electric field like that. And now I'm going to use the dispersion relation of electromagnetic fields and write minus I Ka, where K is the wave vector of the electromagnetic radiation. And I'm just using the usual dispersion relation. Omega c is K. All right, so I can relate the absolute value. Can relate the absolute value of the vector potential directly to the electric field, the strength or the magnitude of the electric field, by dividing the electric. Okay, if I take the absolute value, the I is gone, and the minus I. So I have 2e over c. Now the absolute value of A, this is E divided by K. But if I divide by K, that means I divide by 2 pi and multiply by lambda. That's the wavelength of the light. Right? I'm replacing K by 2 pi over lambda. Okay. And now I'm using a trick here. The expectation value of the momentum operator in a hydrogen atom is well approximated by alpha MEC, where alpha is the fine structure constant, 1 over 137. So now, let's pull all that together. That's 1 over pi alpha. Now, E lambda E divided by MEC squared. Now, what is this? Well, MEC squared, the rest energy of the electron, 511 kiloelectron volts. Now, E times lambda times E, small e times large E, that's the work done by the electric field on the electron. Sorry, no, that's the force exerted by the electric field on the electron. Times lambda, this is force times length, so this is work. This is work done by the electric field on the electron. So you see that the ratio of these two terms here, right? The vector component contribution and the momentum contribution relates as, or it has the same ratio as the work done by the electric field on the electron divided by the rest energy of the electron. The work done along one wavelength of the incident radiation. This is an extremely small number, for example, for visible light, right, where the typical energies are fractions of electron volts or electron volts. So this is typically very much smaller than 1, and then I can make this approximation that I've made. All right, but keep in mind that first of all we are working in this gauge here. We are proceeding under the assumption that this number here, this ratio of terms, is very much smaller than 1, so that I can just neglect this term once I evaluate the perturbation Hamiltonian. Okay. So now if you pull this together, you get E over MEC times A times P. And we are back here, right? I have factored out the omega t dependence of the phase of the vector potential. That's why I'm writing V here instead of H1. But there is a spatial dependence of the phase still left that we have to deal with. Okay. What do we do with that? We neglect it. So now the next assumption I'm going to make is this. Do you accept that? Why could this be good? I mean, it is permissible if k times x is very much smaller than 1. So x, or the typical range within which x varies, is a Bohr radius. That's 0.5 angstroms. That's 0.5 times 10 to the minus 8 centimeters. The typical length scale of k is 1 over lambda, right? So I'm comparing the Bohr radius to the wavelength of the electron. The wavelength of the incident radiation. The wavelength of the incident radiation will be on the order of several hundred nanometers. Right? That's a few times 10 to the minus 7 centimeters. No. A few times 10 to the minus, it's on the order of 10 to the minus 5 centimeters. And we are comparing this to a Bohr radius, which has on the order of 10 to the minus 8. Right? So k times x typically within a hydrogen atom and studying visible light is going to be on the order of 1,000 or less. And then this assumption is not so bad. This is called the dipole approximation for reasons that you will see later. Dipole approximation. So now let me recollect what we have done. We started with Schrödinger's equation and derived from that, we did not derive this, but I quoted this evolution equation here for the expansion coefficients of the perturbed state in terms of the unperturbed states. All right, from that, by integrating over time, you directly get Fermi's golden rule. This is what we are going to operate on. Now, looking at the perturbation operator, we first had to have a look at the conjugate momentum of an electron in an electromagnetic field. We developed that under the assumption of Coulomb gauge and phi equals 0. That's a choice of gauge that we can make. This is not an approximation, but gauge fixing. Okay, next, we are going to ignore terms of order a square, so vector potential square, in the perturbing Hamiltonian. This is legitimate for the reasons that I have sketched. And then we are making the dipole approximation. Right? Studying cases where the wavelength of the light is very much larger than the atom itself. Yeah, Tobi.
I'm just confused. If we are ignoring terms of order a squared, why do we need to write capital B operator in the definition of the perturbation operator? Does that would contain the terms a squared?
I messed this up, I'm sorry. If I write the kinetic momentum such, which I didn't want to do, this is just a small p here. Sorry for that. All right, and now let's move on. So now we have a recipe of what we have to do. We need to evaluate the perturbation operator V under all of these approximations between states n and m. We could, for example, have a look at the hydrogen atom, and n and m could be collections of quantum numbers that describe states in the hydrogen atom. The hydrogen atom you usually need 4 quantum numbers, right? N, L, M, and S, where S is the spin quantum number. I'm not going to distinguish between spin up and spin down because I neglect the coupling of the spin to the magnetic field of the nucleus. So I have 3 quantum numbers in a hydrogen atom, N, L, and M. And N and M, for example, that could be collections of N1, L1, M1, and N2, L2, M2 for states between which I want to look at radiative transitions. All right, so what do I need to do? I need to evaluate now I'm dropping already the spatial dependence of the phase here. So I need to evaluate this expression here. Did I get all the numbers right? I hope so. Now, of course, you could directly proceed, right? You could insert states N and M and move on, evaluating either this expression in momentum representation, in which P is just a factor, or in location representation, where P would be minus I H bar gradient. Perfectly fine. But let me do something different. Let me first have a look at this commutator here. Okay, H0 will have a kinetic term, P squared over 2m, and it will have a potential term that will only depend on x. That's going to commute with x. I'm going to ignore that. So this is going to be this. All right. So this is going to be x commuted with p squared. So this is 1 over 2 me p times xp plus xp times p. That's the derivation property of the commutator that I'm using here. Right? It's the product rule for the commutator. I'm doing that because x times p, of course, this is just I h bar. It would be I h bar in one dimension. In 3 dimensions, it's I h bar times the unit matrix in 3 dimensions. Right? xi commuted with pj is I h bar delta ij. That's the same thing as I've written down here. Same thing here. So you see, this is just going to be I h bar over me times the unit matrix times the momentum operator. So it's just going to be I h bar divided by me times the momentum operator. In other words, I can replace the momentum operator here by this commutator, which looks like a complication, but it is a simplification. So I can write this as m e divided by mec. All right, now a0 me divided by I h bar commutator. So I can do that. And once again, right, this is a vector with a scalar product multiplied with this vector here. All right, but now this is a simplification because now we have the unperturbed Hamiltonian acting on the unperturbed states. And these are energy eigenstates, right? So we just get the energies out. And what I'm getting here is if I pull all the remaining constants out, is minus I e divided by h bar c. The me cancels. Now I take an absolute value of the amplitude of the vector potential and take its direction to be a polarization direction E. Right? Because obviously this transition depends on the polarization state of the incoming radiation. Okay, so these two together are the vector A0. And now, let me do it like that. It's perhaps even more obvious. So now, I'm writing out the commutator. And of course, H0 is Hermitian, so it can act left and right. So in the first term, it's acting to n on n and gives me an energy En times n. In the second term, it's acting left and gives me an energy Em times m. So what remains is just the energy difference, En minus Em. I'm dividing this by h bar, so that just gives me an omega Nm. So this is minus I E omega Nm divided by C, with the definition of omega Nm written down here. Now, A0 E polarization vector M X N. This is a very beautiful result. First of all, suppose N and M have equal parity. Right? They react on spatial reflections in the same way. X, of course, has negative parity. So if I integrate over that, I will, if I carry out this scalar product, this will be 0. Let me write this down. So what I have to do in order to evaluate these terms in location representation is d3x, wave function psi m star, so the wave function of that state, times x. I'm in momentum, sorry, I'm in location representation, so this x operator is just a factor x, psi n. That's the scalar product. Now, if psi n and psi m have equal parity, the product psi m star times psi n will have even parity, then the integrand will have odd parity and will vanish. Right, so only if the product psi m star and psi n has odd parity, this is going to give a result different from 0. That's of course the origin of the selection rules. Right? Which transitions are possible? Only such that change parity. Right? And this gives rise to the usual selection rules. All right, this is what we have to carry out at the end. Now, suppose we pull this factor E, the electric charge of the electron, into this matrix element here. Then we replace the location operator x, or position operator x, by E times the position operator. So I'm going to replace distance by charge times distance. I'm calculating a dipole moment of the between these two states. This is why this approximation here is called a dipole approximation. So we can write this as well as omega nm divided by c, a0 e times, okay, now dipole matrix element between n and m. Let me just write it in this way here. Right? Okay, so we have to evaluate this dipole element here in all these approximations in order to get our transition matrix element. And now, of course, we can pull everything together and insert the result into Fermi's golden rule. Now, what do we get? We get a prefactor of 2 pi over h bar square. Then we get confused. We get the square of this here. A0 square omega nm square divided by c square. All right, now E times the nm. Now this looks confusing, right? This is the expectation value of the vector operator d. Of that, I will have to take the scalar product with the polarization direction of the radiation, and this is going to be squared times the delta function. That's our main result, right? And now I have to evaluate the dipole matrix elements. However, suppose we have arbitrarily polarized incoming radiation. What does that mean? Right? This means that the polarization direction has no correlation with the dipole moments of the irradiated atoms. This will be the usual case. Then I will have to average this over all possible relative angles between E, the polarization direction, and the dipole operator, over all squared cosines of the angle, in fact. And that's going to give a factor of 1/3. And so if I average over polarization directions, I can simply write that. Is that factor of a third mysterious to you, or do you want to see it? So I just need to average the cosine mu of the angle theta between these two vectors. So I have to carry out this integral here. Right? The factor of a half normalizes the otherwise flat probability distribution of the angle cosine mu. Mu square integrated is mu cubed, evaluated between, mu cubed divided by 3, evaluated between plus and minus 1 gives 2/3, divided by 2 gives the third. This is why the 1/3 appears there. So that's the polarization averaged transition rate. Then of course I can also cancel that here and just take the absolute value square of the dipole matrix element. All right, now finally I would like to convert this to a cross-section, a transition cross-section between states n and m. And in order to turn this rate, gamma, to a cross-section, I will have to divide by the current density of incoming photons. So I'm using sigma equals transition rate divided by something. Now, something is given by the pointing, the absolute value of the pointing vector of the incoming radiation divided by h bar omega. Because the absolute value of the pointing vector is the energy per unit time and area carried by the electromagnetic radiation. The number of photons that this carries is given by this divided by the energy of a single photon. Right? So if I, Now let me write down the absolute value of the pointing vector, c over 4 pi times the absolute value squared of the electric field. I'm multiplying this h bar omega upstairs here. And now I need finally the relation between the electric field and the vector potential. If I take the square here, any phase information in the vector potential will fall out. So this will be A0 square. So I can write this as gamma h bar omega c divided by 4 pi k square, but k square is omega square over c square, A0 square. So in that way I can normalize the A0 dependence out of the transition rate. So the A0 square is going to cancel, and I can continue as follows. So first of all, this is 4 pi times c times h bar divided by omega. These are these factors all together here. And then I have gamma divided by A0 squared. But gamma divided by A0 squared is 2 pi over 3 h bar square omega nm square divided by c square. Now, the rest is quantum mechanics, right? Expectation value of the dipole operator between states n and m times the delta function here. Okay. Now let's just pull this together and then have a break. We have 8 pi square divided by 3. This almost looks like the prefactor of the Thomson cross-section, but it isn't. I'm sorry and disappointed. All right, now we have omega nm squared divided by omega. And what remains in the denominator is just an h bar c. All right, this is the cross-section. Now, very often, instead of this omega nm squared divided by omega, you just find an omega. So people cancel the omega and m with the omega. You can do that because this delta function here sets the two equal anyway. We will later replace the delta by something else. So it's safer to leave it like that. But very often, as I said, right, you just find in place of this a factor omega nm. All right. This is the radiation cross-section under the assumption that we've made, right? Dipole approximation and the approximation that the square of the electromagnetic vector potential does not significantly contribute. We saw that you get non-vanishing cross-sections here only if the initial state and the final state have different parity. This gives rise to the selection rules. Everything not allowed by the selection rules is called a forbidden transition. Does it mean it cannot happen? Of course not, because it's forbidden under the dipole approximation. So it's a forbidden dipole transition. This means that in order to evaluate any finite transition probabilities that you still may have under an extension of the dipole approximation, right? You then have to go to the quadrupole approximation, and under that approximation, forbidden lines will again be allowed. Okay, so it's part of the confusion that is characteristics for astronomy and astrophysics. Right? Forbidden lines are not forbidden; they are allowed, but not under the dipole approximation. Okay, I hope. So what I wanted to do with this derivation here was to connect what you usually find in the astrophysical literature, cross-sections like that, to your knowledge of quantum mechanics. That's what I wanted to do. I hope this worked out. And then we will move on after the break. Break of 5 minutes, please. right. Can we move on? It would be nice to replace these dipole matrix elements here by something that is dimensionless. This something is called the oscillator strength. And you find oscillator strength tabulated for very many quantum transitions. I'm going to show you how to calculate them yourself. But how do I do that? I mean, the dimension of d and m is charge times length. Or of d and m squared is charge squared times length squared. Okay. So first of all, if I divide this by charge squared, then obviously I get a length squared. Beautiful. Suppose I multiply this with 1 over h bar. H bar is an energy times a time, and it's ergs times second. So this is gram centimeter squared divided by second. Okay, so if I divide by h squared, the centimeter squared is also gone, but now I have, by dividing by h bar, a second over a gram. I don't want that. So let's multiply that with the electron mass, and multiply that also with omega nm. Now it's dimensionless. This is not the oscillator strength yet, which is decorated with a factor of 2/3 for reasons I don't know. This is called the oscillator strength. F n m. All right, this is a number that you often find in the literature and in tables and whatever. And so if you now insert the oscillator strength into this equation for the cross section, just have to invert this. So I'm just inverting the prefactor here. Now I can write f n m not complicated, but just confusing. Okay. One of the omega nm's cancels. I can collect terms. The 3 is going to go away. I have 4 pi square left. What else do we have? E square over MEC. If I had E square over MEC square, I would have the classical electron radius. So the rest of the units is an RE times C, classical electron radius times the speed of light. H bar is gone. We just have now a ratio of omega nm divided by omega. We have the FNM, and we have the Dirac delta function. And if you wanted, you could use the Dirac delta function in order to identify omega and m and omega and just drop this factor here as well. And then you have a very simple formula, right? Somebody gives you an FNM from a table or by grace or whatever. And then you just have this number times classical electron radius times speed of light times this delta function, and you have your cross section. All right, this is a common form of in which these cross sections are being brought. Now let me return to our Jupyter notebook here, which I extended such that you can calculate your own oscillator strengths. Now what I'm using is again some material from quantum mechanics, namely the orbital wave functions for the hydrogen atom as characterized by the three quantum numbers n, l, and m. So radial wave function times the spherical harmonics, radial wave function looks as it looks, and everything is scaled by the Bohr radius, which you find here. I guess you have seen that before. Now, what I need to calculate in order to find these dipole matrix elements is just the scalar product, right? The scalar product of final wave function complex conjugate times the location vector times the wave function of the initial state. This is being carried out here. It's this thing. There are some selection rules in there and so on. You can have a look at that. And then finally, by applying the definition of the oscillator strength, you can calculate the oscillator strength. So let's take as one state 1, 0, 0. That's the hydrogen ground state. And the next one is the next excited state, right? 2, 1, 0. I could have taken 2, 0, 0 as well, but okay. Now, if you just calculate this, you find an oscillator strength of 0.13, right? These numbers are the oscillator strength is defined such that the numbers are typically on the order of 1 or 0.1 or a fraction of that. Right? These are very, very handy numbers. Now, should we play a little bit here? No. Selection rules forbidden. Haha, forbidden in dipole approximation. If you insist on having this transition, please, but then you need to calculate the dipole approximation, the quadrupole approximation. Aha, this does exist, and so on and so forth. Right? Okay, I just found this funny. And maybe in everyday life, right, you need to calculate an oscillator strength. Please, go ahead. Right. But now, we need to change this a little bit. And the reason for change is this delta function over here. We would have a delta function if energy and time would be infinitely sharp against each other, but they are not. There's an uncertainty relation between energy and time as there is between momentum and position. Now, if the excited state lives only for a finite time, the transition energy between the initial state and the final state will not be sharp, as the delta function tries to tell us. But then, even frequencies of the incoming radiation very close to, but not exactly omega nm, will be able to excite that state because of the energy-time uncertainty. By the way, why are time and energy uncertain against each other? We have an energy operator in quantum mechanics, but not a time operator. You've learned in quantum mechanics that the commutation relation between two operators tells you the uncertainty. We do not have a time operator, but why is there still an uncertainty between time and energy? The reason is only because the two are related by a Fourier transform, irrespective of whether time is an operator or not. In quantum field theory, you will have an operator for time as well, and then the problem does not occur anymore. Okay, suppose the excited state, the final state M, would have a finite lifetime. What do we have to do? This is why I copied our evolution equation over here again. So this was the evolution equation of the expansion coefficient C and M of the perturbed state in terms of the unperturbed energy eigenstates. Now I'm adding something by hand. I'm adding a decay rate. I'm adding a decay rate to the excited state. That is, I want to modify the time evolution of C and M dot such that C and M can spontaneously decay. I'm doing that because in quantum mechanics, there's no reason whatsoever why the excited state should decay. Right? Quantum mechanics is unitary, and once you have occupied an excited state, it will be occupied forever. In order for this state to decay spontaneously, something must happen. And this something are the vacuum fluctuations of the electromagnetic field within the atom. The vacuum, yeah. This is a quantum electrodynamical effect that we cannot cover within quantum mechanics. And so I'm summarizing this quantum electrodynamical effect, right? The effect of the perturbation due to vacuum fluctuations in the electromagnetic field within the atom. I'm going to summarize them phenomenologically by a decay rate gamma d. Okay? That's the point. Now, if there is such a spontaneous decay, then what are we going to do with that? Well, first of all, I'm going to add this term to the other side and multiply the whole equation by an exponential. I want to get C and M plus gamma d over 2 I multiply this by exponential to the power of plus gamma dt over 2. And then I have on the right-hand side the unchanged expression that I already had before. Okay, good. But now, the left-hand side is a time derivative. This is the time derivative of C and M e to the gamma dt over 2. Okay? Just carry out the time derivative and you're there. Yes?
Wouldn't you need that factor on the other side as well?
Yes, 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 yes. Thank you. Haha, of course. Yes. All right, so that's a time derivative equal to that. But now I can again integrate over the whole thing. I can just integrate the right-hand side in order to get the left-hand side. So from here I'm getting C and M e to the power of gamma dt divided by 2. This is equal to minus h bar omega. Okay, let me just write the expectation value of V and M, right? Just to abbreviate this matrix element here. Now I integrate over this term and I get this. And I'm imagining that at time 0 I'm starting to irradiate the atom. So then I have to subtract the exponential evaluated at time 0. Now I'm multiplying the exponential factor back to the other side. I'm going to cancel the I as well. Okay, now I multiply by e to the minus gamma d t over 2 so that it goes away here. But then we have minus e to the power of minus gamma d divided by 2 times t. Divided by, now I've cancelled the I, so this is now omega nm minus omega minus I times gamma d over 2. Okay, now look at this. For long times, this is going to die. And this just goes away, gives 0. If I take the absolute square in order to get the transition probability, this phase factor will also go away. But I will get the square of that instead of a delta function. Okay? So Cnm absolute square, that's going to be absolute square of the transition matrix element divided by h bar squared. And now 1 over omega nm minus omega squared plus gamma d squared over 4. And this means that we now get a transition rate that looks different from what we had before. Let me write this down here. So the transition rate according to Pauli's golden rule, this is now going to be 2 pi over h bar squared, absolute value of the perturbation operator squared. And now a line profile function instead of the delta distribution. The line profile function depends on omega in order to replace the delta function must be normalized to 1. Right? And for that, I'm going to write so this is going to be the real line profile. Instead of being razor sharp, like the delta function was, it's going to look different. If gamma d is very small, it will only be large for omega very close to omega nm. This factor of 1 over 2 pi, this amplitude gamma d, are chosen such that the integral over omega over this thing is going to be 1, right, in order to normalize that. This is called the Lorentz profile. And it's going to look like that. It's like a resonance curve, right? Like the resonance curve of a damped harmonic oscillator. Okay? This is what spectral lines really look like, right? Not razor sharp, but in order, due to their finite lifetime, due to quantum electrodynamical vacuum fluctuations, they are going to be broadened. The gamma d is called the natural line width. All right. Now we are one step further, right? The rest of the derivation is completely unchanged. Just in the cross-section, for example, replace the Dirac-Delta distribution by the Lorentz profile, and you have the cross-section, including the damping that gives rise to the natural line width. But usually, the natural line width is still very small, right? The lines are still very sharp. Okay, but there is another effect. There's another effect that gives rise to the decay of an excited quantum state, and that is if one atom collides with another. Right? Then this collision can pass energy from the excited atom to an atom in its ground state, and therefore also reduce the lifetime of the excited state. And if you go through the derivation, which you find in the lecture notes, for example, then you find that gamma d is just replaced by gamma d plus gamma c. Gamma c is the collision rate. Right? It's the rate by which atoms are de-excited by collisions with other atoms. And that rate, of course, depends on the density of the gas that contains the excited atoms. It also depends on its temperature. But this gives rise to collisional broadening. Collisional broadening. All right. So we have two of these broadening effects, of these damping terms. One is due to the natural de-excitation due to quantum electrodynamics. That gives rise to the natural line width, which is still very narrow. The other one depends on how dense and how hot the gas is. It gives rise to collisional broadening. The effect on the spectral line is going to be exactly the same, except that the two damping rates, the collisional and the natural one, will add. And then you will have the Lorentz profile. All right. This is not going to be all. Because we have another damping effect. No, sorry, another broadening effect. Because what we have looked at now were atoms in their rest frame. Now, of course, if they move with respect to us, their lines are going to be red or blue shifted, depending on whether they move towards us or away from us. Sorry, the other way around. Away from us will be red shifted. This we will also have to take into account, because suppose we are looking at a gas cloud like this, and the atom we are observing at the moment is going to move away from us. Then the frequency at which we see its spectral line is going to be redshifted, or blue shifted the other way around. So we are not going to see the line at its original location, but at a Doppler shifted or redshifted location. And this we also need to take into account. So how do we do that? First of all, the frequency where we observe the line is going to be the frequency in the rest frame, 1 plus the parallel velocity, the velocity component parallel to the line of sight, divided by c. Right? If this parallel velocity is positive, if it's moving away, then the frequency is lowered. Sorry. All right. this is the non-relativistic approximation to the Doppler shift. Right? You can also make this precise by using relativistic motion. Maybe we'll ask you to do this in a problem sheet. Okay, so this is where we will actually see the emission line. Now let me study this effect at the example of a delta sharp line, and later extend this to the Lorentz profile. So this is going to change to, by the Doppler effect, to omega nm, that's the angular frequency of in the rest frame of the atom, times 1 minus v parallel over c minus omega. This is one way of looking at that. This would be applying the Doppler shift or the redshift to the rest frame of the atom. But actually what I want to do is something different. I want to see at what observed frequency I will observe the line. So I need to apply the Doppler factor here. All right. Now what will I really see? I will see a superposition of these spectral lines weighted by the probability to find the velocity v parallel. So there will be a certain probability for the parallel component of the velocity, and I will have to weigh the spectral line in this way here. Okay. Now let me modify this a little bit. Let me use the identity that delta d of a times x is 1 over a times delta d of x. Right? That's the transformation rule for the Dirac delta distribution. And write this as some quantity here, which now has also the dimension of a velocity plus v parallel. Now, as you see, this is now the convolution, the mathematical operation of a convolution here between this probability distribution for the electron velocities, or the atom velocities, and the line shape for each individual atom. So this means that the actual line profile, yeah. Ah, that's true. Yeah, I'm factoring c omega over c out from the delta function, yes. And then c over omega remains here. All right, so I have omega over c. Now, I'm replacing the delta function again by the line profile function here. which I now need to transform to the velocity. Right, so I need to transform this to in the same way as before. A. All right. The essence is that ultimately I will have to replace the line profile function, which we just saw is a Lorentzian profile, by the convolution of the velocity distribution and the line profile function. That's the key point, right? So all the individual atoms are moving with different velocities. Their velocities are distributed according to some probability distribution. What I'm going to see is therefore not a single Lorentz profile, but a superposition, a weighted superposition of Lorentz profiles, weighted with a probability distribution. This weighting is reflected by this convolution here. Now you can express this in a different way. We have transformed the frequencies to velocities. You could also transform the velocities here to frequencies. Either way, it just gives different prefactors. Okay, this is the key point of what I wanted to tell you now. Now, suppose the velocity distribution would be Gaussian. It doesn't need to be, but if the distribution of atoms is thermal, characterized by a certain temperature, then the probability distribution P of V would be a Gaussian. Then you would have a convolution of a Gaussian and a Lorentzian. And this object occurs so frequently that it got a name. It's called the Vogt profile. So if P of V is Gaussian, then phi is called the Vogt profile. A convolution of a Gaussian with a Lorentzian. And if you want to know what that looks like, the Vogt profile has essentially unchanged wings as the Lorentzian. If you are far away from the width of the Gaussian, it differs from the Lorentzian in the center by developing a Gaussian, this is crude, right? By developing a Gaussian core. And this is what spectral lines typically look like. And you do have not a delta function, not a Lorentzian profile, but a Vogt profile. And this is very important for interpreting spectral lines. Okay, so starting from the calculation of the cross-section, right, that we made earlier, where I essentially wanted to introduce the notion of the oscillator strength and show the expression for the cross-section. I wanted to explain why this delta function here, or delta distribution, that would argue for a razor-sharp spectral line, has to be replaced. And it has to be replaced in 3 steps. The first is excited states decay spontaneously because they are perturbed by quantum electrodynamical vacuum fluctuations. This gives rise to this gamma d here, to the natural line width, which is still very small. In addition, you have a collisional line width, which comes from the fact that by collisions you can also de-excite excited states, right? Because collisions can pass energy from an excited state to an unexcited state. So in fact, you will have to replace the natural line width by the sum of the natural line width plus the collisional line width, which depends, well, that's the decay rate due to collision, so you need to calculate this by calculating the collision rate. The collision rate will be given essentially by the Bohr radius squared, that's the cross-section of an individual atom, times the density, times the velocity of the atoms, right? You can calculate the collision rate. You can estimate it roughly in this way. Okay, if you take these line widths, these line broadening mechanisms into account, the delta function changes to a Lorentzian. I've shown you how this comes about. And in addition, because the electrons are moving, you will have to convolve the individual line profiles with the velocity distribution of the atoms. Now, the velocity distribution can be anything, and could also be a power law, for example. But if it is thermal, then the line profile will be a Vogt profile, right? The convolution of a Gaussian with a Lorentzian. Okay, this is what I wanted to tell you today. Now, unfortunately, Wednesday is a holiday, and this shortens the week a bit. I would like to continue next time by illustrating what happens if you now observe spectral lines and want to know, or you want to interpret the width of the spectral lines that you observe in terms of the number of absorbing atoms. And ultimately you would like to find out, or maybe you would like to find out, how much absorbing material is there? Now, how do you get this out of the spectral line? This is what I wanted to speak about next time. Then, of course, the shape of the spectral lines is very important, and this gives rise to certain so-called curves of growth that we will have to discuss. Remember the approximations we have made. They were quite substantial. Right? We fixed the gauge. Okay. We assumed that the vector potential squared can be neglected compared to the momentum within, or the coupling term between the vector potential and the momentum within the atom. This may or may not be the case, right? If you had reactions between, or if you wanted to look at cross-sections of very energetic photons with atoms, for example, this may be a shaky assumption. Also, we made the dipole approximation, right, assuming that the wavelength of the light is large compared to a characteristic length scale of an atom. Again, this may or may not be true. It gives rise to selection rules that I told you. The selection rules may or may not apply. If they do apply, you do not necessarily get a cross-section of zero, but you do get a cross-section of zero in the dipole approximation. You may still have allowed quadrupole transitions. We came across the notion of an oscillator strength. Here's a recipe how to calculate them. All right. There is one more thing you will encounter on the next problem sheet. And that is, if you have a transition between a multiple initial state to a multiple final state. Right? There could be a degeneracy in the occupation number of the initial state and of the final state. You will have to multiply the transition cross-section by these multiplicities. Just because if you have higher multiplicities of the initial state and the final state, the transitions become more frequent. If the final state is in the continuum, in other words, if you have kicked the atom so hard that it loses its electron, you will have to multiply with the number of states for the final state. This is a complication that will occur in the problem sheet, and we will explain this to you. Then you can calculate your own version of the bound-free transition of the hydrogen atom, for example. This is a relatively easy calculation which you find in the lecture notes. We will still pose it as a problem because I would like you to calculate this in a different way than the lecture notes. Okay? Have fun with that. I'm tempted to say have a nice weekend, but it's Monday at 11. We are going to meet again next Monday. Wednesday is a holiday. Thank you for the attention.